My name is Ayodele Akiadamu and I'm a Nigerian. This is my first video on finite element method of one-dimensional problem using MATLAB and Ansys. This is also my introduction video. I intend to share my little knowledge which I acquired recently on the topic of finite element procedure for solving structural engineering problems. I plan to treat several problems applying finite element procedure. The finite element method is one of the numerical methods of solving structural engineering problems. This method can be applied to diverse problems in civil engineering. I plan to treat one-dimensional problems such as bars in compression or in tension or in combination. I plan to cover two-dimensional problem such as plate analysis using the constant strain triangle element CSTS. That's what they call it, the constant strain triangular element. Under the 2D plate analysis, steel plates under loading will be analyzed using the plane stress condition. Also, the 2D finite element procedure will also be applied to beam analysis. I was surprised when I learned that the 2D finite element procedure can be used to analyze beam structure. So I'm going to illustrate how we use 2D finite element procedure for beam analysis on MATLAB and on Ansys. Also, truss structure is going to be analyzed using the finite element procedure. Truss structures such as the 2D structure, the plane truss, the 2D plane truss, and also 3D plane truss will be analyzed using the truss finite element. Also, a special type of 2D plane truss is going to be analyzed. That is a 2D plane truss with inclined support. For this type of truss with inclined support, we need to apply a concept called the multi-point constraint model. So I'm going to illustrate how this multi-point constraint model is applied to truss analysis using the finite element approach. Also, beam analysis will be analyzed generally with by using the beam finite element. That's the normal procedure, not using the 2D finite element procedure. We're going to analyze beam using the finite elements, using beam finite element. Also, frame will be covered. Frame analysis will be treated in my subsequent lesson using the frame finite element. The tool for my lessons for this topic are number one, Ansys program and the MATLAB program. These are the tools which I'm going to use to explain the finite element procedure of solving structural engineering problems. The basic structure of all my lessons is this. A structural problem will be presented, then the numerical procedure will be explained and calculated by using MATLAB as a calculator. And lastly, the method and procedure of modeling and solving this problem will also be explained and demonstrated on Ansys program. I will be starting my series of lessons on finite element procedure from one-dimensional problem. In my subsequent lesson, I'm going to treat about 5 to 6 one-dimensional problems. The one-dimensional problem is the simplest problem you can solve using the finite element procedure. In my next slides, I'm going to show you the different one-dimensional problem which I'm going to solve using the finite element procedure. This is one of the problems that will be solved using the finite element procedure. This is a bar element under 160 kilonewton tension load, as you can see. It has two parts, part 1 and part 2. Part 1 is the part 1, element 1 is between node 1 and node 2, and the second part is between node 2 and node 3. So it is required that the area deformation at node 1, at node 2, and node 3 be calculated using two linear finite elements, and also the stress in each element, element 1 and 2, be also found. The material and geometric property of the problem is also given as A1 E1 and A2 E2, where A is the cross-sectional area of each finite element, and E is the Young modulus of each element, and the Young modulus in gigapascal units. To solve this particular problem using the finite element procedure, we need to convert the problem to an equivalent structure with support. Presently, this problem cannot be solved using the finite element procedure because it has no boundary condition. When I mean boundary condition, it has no support. So we have to convert the problem to an equivalent structure with support. So to do that, I'm going to illustrate this in my subsequent lesson when I'm analyzing the structure. But I'm going to give a quick overview of what I mean by equivalent structure with support. Either you put a support at node 1 that will restrain movement, or you put a support at node 3 that will restrain movement and apply 160 kilonewton load at the end of the member. So if I should apply say a support here, well, and apply a 160 kilonewton load at node 3 is equivalent to applying 160 kilonewton at node 1 and node 3. So this is how this is structure we're going to analyze using the finite element procedure, but it's going to be modified by placing a support at node 1. This problem without support cannot actually be solved, as I've said. The global stiffness matrix cannot be inverted. That's why it cannot be solved. The K matrix cannot be inverted. So we need to convert the structure to an equivalent structure, where we can apply finite element procedure to solve this problem. Moving on to the next slide, we see the next problem that will be solved using MATLAB and Ansys. This problem is actually an extension of the previous problem which I just showed you. However, in this problem, we have two boundary conditions, a support condition at node 1 and node 3. In this problem, it is required to determine the deformation at node 2 and also to calculate the normal stress in element 1 and element 2. The third problem that will be tackled is a problem with contact problem. A problem with contact problem. In this problem, we have a bar element that is constrained at this point, and at the other point there is a 1.2 mm gap between the support and the end of the bar. So in this problem, the applied load at the midspan of the bar will stretch the bar until the node B just touch the wall. Then this support B will generate a reaction force. After the node, that is when the node B touches the wall, The support beam will generate a reaction force which will act on the bar element and change the stress and strain distribution in the body. For this problem, a method in finite element procedure called the penalty approach is perfectly suited to solve this type of problem. This problem will be solved using the penalty method on MATLAB, and also another method, which is a unique method, which was derived by me, will be used to solve the problem on Ansys program. The fourth one-dimensional problem that will be covered is a symmetrical type of problem in which the body is both geometrically symmetric and the loading also is symmetric. In figure A, the geometric and the loading is symmetric about this point. What is on the left-hand side is what is on the right-hand side. So half of the structure can be modeled and analyzed to determine the deformation and stress values. This will be illustrated using Ansys program. We are going to compare the results, the full model analysis and the half model analysis on the Ansys program. The last problem that will be solved in my lesson is this problem shown in the slide. This problem will be solved using MATLAB, using a concept called the multi-point constraint model. However, this problem will not be analyzed using the Ansys program, sadly because of my limited knowledge on multi-point constraint model as it applies to the Ansys program. So these are the 5 or 6 problems that will be tackled using MATLAB and Ansys in my subsequent lesson on finite element procedure of one-dimensional problem using MATLAB and Ansys. Next, I'm going to give a brief introduction of the theories of 1D finite element procedure. I'm not going to go into too much details. I'm only going to show you some of the necessary formulas you need to memorize in solving one-dimensional problem using the finite element procedure. I'm not going deep into the theoretical background of finite element procedure. That is not the aim. It's just to show you the formulas you need in solving this type of problem. First thing you need to know about one-dimensional problem using finite element procedure is that you need to know the formula for the local stiffness element for each one-dimensional element. The one-dimensional element in finite element, there are 2 types. We have the one-dimensional linear element and the one-dimensional quadratic element. The one-dimensional linear element, the local stiffness matrix is defined by this, a 2x2 matrix, while the quadratic element, the local stiffness matrix, is defined by this, a 3x3 matrix. For the one-dimensional linear element, the one-dimensional linear element has 2 nodes, a start node 1 and an end node 2. The quadratic element has 3 nodes. The start node, the end node, and another node at the center of the element. The quadratic element actually provide more accurate result than the one-dimensional linear element. But this quadratic element is seldomly used for manual computation because of the computational complexity. As you can see, you need to manage a 3 by 3 matrix, whereas a linear element, the local stiffness matrix is just a 2 by 2 matrix. So the computational effort for using the quadratic element is far greater than the computational effort you will use for the linear element. So that's why this method, the quadratic element, is seldomly used for solving numerical problem manually. This quadratic element can actually easily be implemented by structural programs like Ansys. This using the quadratic element actually gives more accurate results than linear elements. Um, so what's important here is that you need to know that the local stiffness matrix of a one-dimensional linear element is given by this EAL and this matrix, while the local stiffness matrix of the one-dimensional quadratic element is given by EA over 3L times this matrix. So in one-dimensional problem, the first step you need to do, you need to define your local stiffness matrix of all elements in the model. If you have 3 or 4, if you have say 4 elements, you need to define the local stiffness matrix for each of the 4 elements. Next, you need to understand how the global stiffness matrix of the body is assembled for one-dimensional problem from the local stiffness matrix. This is important. I'm going to explain how to assemble the global stiffness matrix using this image on the left-hand side. In this image is actually a body. Let's call it a body that is loaded at this point at node 2, and it is supported at the top, node 1. The body is divided into 4 parts: 1, 2, 3, 4. And the node point is numbered from the top to the bottom: node 1, node 2, node 3, node 4, node 5. Because the body has 5 nodes, it means our global stiffness matrix should be defined by a 5 by 5 matrix, just because the one-dimensional problem is defined with 5 nodes. So it means that these are our node 1, node 2, node 3, node 4, node 5. The same thing for the column: node 1, node 2, node 3, node 4, node 5. Next, each local stiffness matrix of the body is added to form the global stiffness matrix. That is in order to assemble the final global stiffness matrix. So let's say here we have 4 elements. So we have 4 local stiffness matrices. We have K1, K1, K2, local stiffness matrix, K3, K4. And here we're actually using a one-dimensional linear element. That is a local stiffness matrix with a matrix of size 2 by 2. So how this is assembled, if you look at this K matrix written here, you will notice this similarity. What I circled here is actually the value of K1. And you can see that K1 is added in what position in the global stiffness matrix? It's added at 1 and 2. 1 and 2. Why it is added here is because element 1 is between node 1 and node 2. For element 2, which is between node 2 and node 3, we see element 2 here. We see the local stiffness matrix of element 2 here. So this is the local stiffness matrix of element 2, and you can see it is added at position 2, 3 along the row and 2, 3 along the column, just because element 2 is located between node 2 and node 3. The same thing for element 3 and element 4. So this is how the global stiffness matrix is assembled from the individual local stiffness matrix. In my subsequent lesson, I will be showing you a systematic procedure of assembling the global stiffness matrix by using the MATLAB program. It is very, very easy to assemble this using MATLAB. After we have defined the global stiffness matrix, next we need to define the global force vector. In finite element procedure, there are actually three types of load that can be defined. We have the traction load, the traction force, the body force, and the point load. In this slide, in this structural body, the traction force is actually depicted as T1, T2, T3, T4. The body force is actually depicted here is the self weight of the body of each element, and actually F is actually the self weight of the body in, say, Newton per meter cube per volume. F. And you can in this example, we also see a point load acting at node 2, P2. So you can see the three different type of forces acting on this body. Now, to assemble the global force vector from this example, here the three forces that can be defined in finite element procedure is found in this example. So in assembling the global force vector, we see that element 1 has a traction force of T1. And first, I would actually like to define what the traction force is and what the body force is. The traction force is a line type of load, a line type of force. It is defined as force per unit span, force per unit length. An example of this load is like in beam analysis, like the uniformly distributed load on our beam, or say the friction force that acts over a span between two surfaces. So to form the force vector for the traction force, let's consider element 1. Element 1 and T1 traction force acting on element 1. So the total traction force acting on element 1 is given by T1 times L1. L1 is the distance between node 1 and node 2. So the total force acting on element 1 is T1 times L1. This total force is divided between the two nodes between the elements. Element 1 is, for element 1 has node 1 and node 2. So the load is divided equally between the two nodes. Half of the load goes to node 1, the other half goes to node 2. That's why we have this component here, L1 T1 divided by 2 at position 1, and L1 T1 divided by 2 at position 2. The same thing for element 2, element 3, element 4. You can see L1, L2, T2 divided by 2 at node 2 and L2, T2 divided by 2 at node 3 for the element 2. For the element 3, the same thing, L3 T3 divided by 2, L3 T3 divided by 2. the load are divided equally between the node between the load are divided equally between the nodes of the element. For element 4, we have L1 T4 divided by 2, and we also have L4 T4 divided by 2 at 4 and at 5. The same thing for the body force. However, for the body force, you multiply by the volume and you divide by 2. And the volume is the area times the length. So we have ALF divided by 2 for the element 1 at node 1. And we have A1L1F divided by 2 at node 2. This is for element 1. The same thing is done for element 2, element 3, element 4. You can see this is common A2, L2F divided by 2, A2, L2F divided by 2. This is for element 2. For element 3, the same thing, the same thing. For element 4, the same thing, and the same thing. For the point load, the only point load acting on this body is at node 2. So because the only point load acting on the body is 0.2, at node 2, P2 is written here, and other node we put 0, 0, 0. So these two matrices are added together to form the global force vector. In real life one-dimensional problem, the self-weight of the body is usually very negligible compared to the point load. And also we suddenly don't have a traction force. We only have a point load. So this part, we don't normally deal with it in one-dimensional problem. This is the part we normally deal with. So this is how the global force vector is assembled for one-dimensional problem using the finite element procedure. Next, we calculate the global displacement vector. This is calculated, is not assembled. After the global stiffness matrix K and the global force vector has been assembled, we can calculate the global displacement vector, which is given as the inverse of the global stiffness matrix multiplied by the global force vector. However, unfortunately, K cannot be inverted. So there is however, there is a finite element procedure that can be used to modify the K matrix to make it invertible. We're going to look at this in the next slide. Because the global stiffness matrix cannot be inverted, we need to apply boundary condition, that is support condition, to the global stiffness matrix. And there are two general methods of applying boundary condition in the finite element procedure. We have the elimination method and we have the penalty method. I use illustrative example to explain both method. In the elimination method, if the rows and the column of support DOF number is set to 0, if the rows and column of support degree of freedom, DOF means degree of freedom, is set to 0, then we can cancel the rows and column of that of the global stiffness matrix at that point. For example, we have a global stiffness matrix shown here by K, say a 6 by 6 matrix. Say the support degree of freedom at 1, 2, 3 is equals to 0. So because the support degree of freedom at 1, 2, 3 is equals to 0, that there is support at node 1, node 2, node 3. The K matrix can be modified to form a new matrix, which I define as mod K. So because 1, 2, 3 is set to 0, I cancel the element at row 1, row 2, row 3, and column 1, column 2, column 3. So I only have this remaining. So this is our modified global stiffness matrix. So this is how the elimination method can be used to modify the global stiffness matrix so that it can be invertible. The modK matrix is actually an invertible matrix. We can invert this matrix. The second method of applying boundary condition is the penalty approach, the penalty method. In this method, a large stiffness value is added to some elements of the global stiffness matrix. That is to make it, that's how we make the matrix invertible, by adding a large stiffness to some elements in the matrix. That is where we have support degree of freedom to be equals to 0. Generally, the last stiffness is defined as the maximum element in the global stiffness matrix multiplied by 1000. For example, we have a global stiffness matrix here, a 6 by 6. The maximum element in this matrix is this value here, 19,200,000. So this value multiplied by 10,000 is the stiffness value which I'm going to add to this K matrix. I define C as the maximum I define C as the maximum element value multiplied by 1000. So I'm going to add C to the support degree of freedom of the K matrix. In this example, assume the support degree of freedom is at node 1, node 2, and node 3. So I'm going to add C to K at position 1, 1, that is to this, plus C, position 1, 1, position 2, 2, and position 3, 3, and position 3, 3. So that is why actually this is the modified matrix here, and you see 19.2 times 10 raised to power 11 is added here, and it's also added here. Adding the C value to the matrix actually makes the other values so small. That's why we see 0, 0 everywhere. So this is how we modify the global stiffness matrix using the penalty approach. We add a value, we add a large stiffness at support degree of freedom in the global stiffness matrix. After we have modified the global stiffness matrix and a new global stiffness matrix is formed, which I denote by mod K, we also need to modify our force vector matrix. So in modifying our force vector matrix, the vector element at support degree of freedom is also eliminated in the elimination method. Say we have a force matrix, a force vector matrix defined by this, and say at support degree of freedom, and say we have force support at node 1, node 2, node 3, and node 5. It means that at position 1, 2, 3, and 5, those elements will be eliminated. The numbering of this force matrix is 1, 2, 3, 4, 5, 6. So at 1, at 2, at 3, and at 5, this element will be eliminated, and it will only remain 1000 and minus 1000. So this is the remainder is the modified F matrix, which is given here as this, a 2 by 1 matrix, 1000 with element 1000 and minus 1000. In the second method, the penalty method, the force vector is not modified when the support degree of freedom is set to 0. at the support degree of freedom, we don't eliminate or modify the false vector. The false vector is only modified where we have contact problem. Like in this example, at node B, there is a gap between the support and node B, a 1.2 gap. So the first matrix or vector is modified by adding the value of C, which is the large stiffness. C is defined as the maximum element in the global stiffness matrix multiplied by 1000. That is what C is. You multiply C by the gap. In this example, the gap is 1.2 mm. So C times 1.2, you add this value to the position of node B in the false vector. Say in this problem, this is a node 1, node 2 because there is a point load here, and node 3. So in the false vector at position 3, I will need to add C times 1.2 to the element to the value element of the false vector at position 3 of the false vector. So this is how the false vector matrix is modified using the penalty approach. Now that the false vector matrix has been modified and also the global stiffness matrix has been modified, we can now determine or calculate the modified displacement vector. Like this is the general formula K times Q equals to F. However, because K cannot be inverted, we modify K and we modify F. So K changes to mod K, F changes to mod F. So if we change K and F, our modified displacement vector can be defined as this. The inverse of mod K times mod F false vector. Here mod K is very invertible. So this is how we calculate the displacement quantity for a one-dimensional problem using the finite element procedure. So this is the formula we use. After we've calculated the displacement vector, we can use the displacement vector also to calculate the normal stress in each of the one-dimensional linear elements. Here, the formula for the normal stress is given. The most important equation here is this stress matrix equation given by this. I'm going to do a small sketch here. Assuming we have a body which is defined by two linear elements. This is node 1, node 2, node 3, and this is element 1 and this is element 2. So at node 1, it has a displacement quantity, say Q1. At node 2, it has a displacement quantity Q2. And at node 3, it has a displacement quantity Q3. So for the element 1, the Q vector is Q1, Q2. Well, assuming we are looking at the elements from 1 to 2, we're assuming 1 is the start node and 2 is the end node. For element 2, the Q vector will be defined as Q2, Q3. So here will be Q2, Q3 for element 2. For other elements, it is done in the same fashion. So the stiffness matrix is given by E over L times this matrix minus 1, 1 times the Q matrix. The L is the span of each linear element. The L for element 1 is the distance between node 1 and node 2, while the L for element 2 is the distance between node 2 and node 3. So this formula is very important in calculating the normal stress for one-dimensional linear elements. After we've calculated the normal stress in the linear element, there's also a formula for calculating the reaction at support. In my next slide, I'll show you the formula. So this formula is used to calculate the reaction at support for a one-dimensional linear problem. So the reaction is given as minus C, open bracket, Q Pi minus AI, where C is defined in my previous slide as a very large stiffness, and we define C as the maximum element in the global stiffness matrix multiplied by 10,000. The QPI is the calculated displacement where the support is located. So if the displacement is 1.2 mm, so QPI will be 1.2 mm at that support node. If there is a contact problem at the support location, say there is a gap of 1.2 at that point, so A will be defined as 1.2, which is the gap between the node and the support. So, but where there is no gap at the support, A is set to 0. And when A is set to 0, the reaction formula reduces to this, minus C multiplied by the displacement quantity at that support node. And lastly, in my next video lesson, we are going to look at this problem. This will be our first one-dimensional problem, which we are going to solve using MATLAB. The finite element procedure will be applied to calculate the deformation at node 1, at node 2, and at node 3, and also the stiffness, the stress in each of the elements, element 1 and element 2, will also be found. I would like to say the finite element procedure is a systematic procedure. Once you know the formulas to use, you just have to follow a systematic approach to get to the final answer. It is not difficult at all. I'm going to guide you through the process of using the finite element method in solving different structural engineering problems. Now I have come to the end of this lesson. Thank you so much for watching my video on YouTube. Next video will be uploaded maybe in 2 to 3 days time. Have a nice day.